We will take down another problem based on bar magnet placed in a uniform magnetic field. A bar magnet of magnetic moment moment 1.5, a bar magnet of magnetic moment 1.5 joules per Tesla or ampere meter square. Ampere meter square lies aligned, the unit is ampere meter square, lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. What is the amount of work required? Question number A. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment Question number 1. Normal to the field direction. Question number 2. Opposite to the field direction. And question number B. What is the torque on the magnet in cases 1 and 2? What is the torque on the magnet in cases 1 and 2? Okay, let me read once again. A bar magnet of magnetic moment 1.5 ampere meter square lies aligned with the direction of a uniform magnetic field of 0.22 Tesla. What is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment normal to the field direction, opposite to the field direction? What is the torque on the magnet in cases 1 and 2? Now the bar magnet of magnetic moment is given magnetic moment of the bar magnet M is 1.5 ampere meter square, lies aligned with the direction of a uniform magnetic field, so B is given 0.22 Tesla, and the position is in such a way that the magnetic moment and the direction of uniform magnetic field are same. If magnetic moment is in this direction, the uniform magnetic field also in the same direction. So theta I, or initial position, is 0 because magnetic moment and magnetic field are aligned to each other. Now the question number A is, what is the amount of work required by an external torque to turn the magnet so as to align its magnetic moment Normal to the field direction, opposite to the field direction. Now first we will write the equation for work required, or work required to turn the magnet from initial position theta I to theta f is given by work required as W as mb into cos theta I minus cos theta f. Initial position, final position. Theta I is initial position, theta f is final position. Now question number 1. Normal to the field direction. Now the magnetic moment is making an angle 90 with the direction of magnetic field. If this is the direction of magnetic field, magnetic moment is in this direction. So the angle is 90 degree. Initially they were parallel. So now theta f is 90 degree. And theta is anyway it is 0. Because to turn the magnetic from the initial position to a position where m makes an angle 90 with the direction of the magnetic field. W is equal to mb, m is 1.5 multiplied by b is 0.22 into cos 0 minus cos 90. Cos 0 is 1, cos 90 is 0. So it is 1.5 multiplied by 0.22. Yes, the answer is 0.33 joules. The work done in turning the magnetic in turning the bar magnet from its initial position to another position wherein the magnetic moment is perpendicular to magnetic field is 0.33 joules. Now what is the second case? Case number B or 2. Opposite to the field direction. Opposite to the field direction. Here if B is in this direction, now magnetic moment is in this direction. The angle between them is 180 degree. Therefore the final position or theta f is 180 degree and initial position is anyway it is 0, because from its initial position to a position where magnetic moment and B are opposite to each other. Now W is mb, that is 1.5 into 0.22 into cos 0 minus cos 180. Cos 0 minus cos 180. We know cos 0 is 1, cos 180 is minus 1. So this value is 1 and this value is minus 1. So 1 minus minus 1 will be 2. Therefore it is 1.5 multiplied by 0.22 into 2. This will be 2 times the previous case. 0.66 joules. Now the question number B is to determine the torque acting on the power magnet in these two positions. What is the torque on the magnet in cases 1 and 2? Now torque is given by torque tau as mb sin theta. So case 1, when B and M are perpendicular to each other, theta is 90 degree. Torque is mb sin theta. M is 1.5 multiplied by 0.22 into sin 90. Sin 90 is 1. Therefore, this is 0.33 Newton meter. Newton meter. And case number 2. Here M and B are opposite to each other. B is in this direction, M is in opposite direction, so the angle between them is 180 degree. So torque is mb sin theta. Theta is 180. If theta is 180, sin 180 is 0, and hence sin 180 is 0, or torque in this position is 0. Not 0 degree, sorry. Torque is 0 Newton meter. No torque is acting in this position. When theta is 180, torque is 0. When theta is 90, torque is 0.33 Newton meter. Hope you understood this problem. We'll take some more problems in the coming class.